Alright, we're going to take a look at evaluating the limits from Cal1 what are in indeterminate form. So for us that's really 0 over 0. There might be some rare instances where you might have some sort of plus or minus infinity over plus or minus infinity, but most of that stuff you'll see a little bit more in Calculus 2, where you have access to something called L'Hopital's rule. Anyways, the first thing we're going to always try to do when we're evaluating a limit is, can I just directly substitute in? And if we look at this one, if I plug in 3, I'm going to get 9 minus 9 over 3 minus 3, so I get 0 over 0, so we can say that that is an indeterminate form of 0 over 0. And we have a couple of different techniques. Most of them involve some sort of algebra. Sometimes it's some factoring, sometimes it's some clearing some fractions, sometimes it's rationalizing a numerator. And then we'll have a couple of special trig limits too. So this one we're going to go ahead and factor it, and we can say it's algebra time. Alright, so difference of squares upstairs. It's x minus 3, x plus 3. And we can go ahead and divide out the like factor. So those divide out, and this is now equal to the limit as x approaches 3 of x plus 3. Now we can directly substitute in, so that's 3 plus 3, which is 6. And it seems like the other 3 got cut off there. Okay. I think you can probably see it. I think I'm just zoomed in on my screen. Alright, let's go do another one. So let's try limit as x approaches 1 of the square root of x minus 1 over x minus 1. So if I plug 1 in, that's the first thing I'm going to try. Square root of 1 is 1. 1 minus 1 is 0. And then, of course, on the bottom, 1 minus 1 is 0. So this is indeterminate form, so we might be a little bit stuck. What we're going to go ahead and do is we're going to rationalize by the denominator here, and we're just going to use the conjugate. So the conjugate of a minus b is a plus b, and that's just our difference of squares right there. So that's what we're going to get going there. That's going to get rid of the square root, and things are probably going to work out fairly nice for us. So let's see what happens. So this is kind of the general strategy here. All right, so we will multiply the top by the square root of x plus 1. That's the conjugate. And anything we do to the bottom, we got to do to the top. Or anything we do to the top, we do to the bottom. We'll go ahead and FOIL out on the top, so that'll be square root of x squared minus 2 square root of x minus 1. And no, that's not right. That's a mistake. That shouldn't be there. So this should be minus 1, because it is a difference of squares, so that is an error. Okay, but I think we can probably fix that. So we're gonna fix that as we go along. All right. Okay, so this is equal to the limit as x goes to 1 of x minus 1, and then x minus 1 square root of x plus 1. And we got like factors of x minus 1, so those will go ahead and divide out. And now we're ready to go ahead and just evaluate this. So plug in 1, and the whole thing is going to be equal to 1/2. That's what that limit is. Later on we'll do some stuff with this again when we get into derivatives. You know, this will be a little bit familiar. Okay, let's look at another one. So limit as h goes to 0 of x plus h squared minus x squared all over h. And if I directly substitute, I'm going to get x squared minus x squared on top and 0 on the bottom. So we're going to have to do something. Let's go ahead and FOIL out the top. It's going to be x squared plus 2xh plus h squared minus x squared all over h. We can say so long to those x squareds. So goodbye x squared. We're left with 2xh plus h squared all over h. We can divide everybody by h. So we will be left with 2x plus h, no longer in danger of dividing by 0, and we don't have 0 over 0 or anything like that. So we can go ahead and directly substitute in 0. And this whole thing is just equal to 2x, and that's going to be pretty familiar with the x squared later on. Alright, let's work through 2 or 3 more. Let's do a more exciting one. So we got 1 over x plus h minus 1 over x. And that's all divided by h. And this time what we have is it's a complex fraction because we have a fraction within a numerator or denominator of another fraction. And again, if I plug in 0, I'm going to get indeterminate form 0 over 0. So I'm going to have to do something, and let's go ahead and clear this complex fraction. So the LCM of the top is x plus h. So I'm going to multiply both the numerator and the denominator of the big fraction by x plus h. And then when we clean that up, we'll have x minus parentheses x plus h all over hx and then x plus h. And the x's will go ahead and cancel, and we'll have minus h over hx, x plus h in parentheses. Go ahead and divide out those h's. And we have negative 1 over x plus h, and happy times, we can go ahead and plug in 0 in for h. Not a problem anymore. Notice once we evaluate, we drop the limit symbol because we're no longer taking the limit. And this will be also a very familiar thing to you later on with 1 over x having this thing. So our limit here is negative 1 over x squared. So let's do some with some trick. So limit as x goes to 0 of tangent squared x over x. So tangent squared is sine squared over cosine squared. Sine squared of 0 is 0. So we got 0 over 0. So this is an indeterminate form. And one of the strategies we can do with trig is try to break things down into sines and cosines. Maybe some stuff will cancel. Maybe we'll have some sort of special limit. So we do have a special limit that we may end up using here. It's the limit as x goes to 0 of sine x over x, and that's equal to 0. And I did do a proof of this on another video. It's probably called application of the squeeze theorem. So you actually use the squeeze theorem to prove this theorem. So I think we're going to end up getting something like that, where we have sine of x over x as x goes to 0. But we're going to have to work at this a little bit. Okay, so we're going to rewrite this. So it's just going to be sine squared x over cosine squared x, and then the 1 over x. And then what I'm going to do here is I see like I almost have the sine x over x bit, and that x in the denominator is kind of giving me some problems. So if I can put a sine x on top of it, then I know what that limit is. So limit as x goes to 0, and we have sine x times 1 over cosine squared x. I know what both of those limits are. I can plug in 0 and have no problems. And now with the sine x over x, I know what that limit is. So we can directly substitute in for the sine and the 1 over cosine. Notice we dropped the limit symbol. And then we know that the limit of sine x over x is 1. Well, ends up being not that exciting because sine of 0 is 0, so the whole limit after all that hard work was just 0. Okay. We're going to look at one more limit with the trick. So we're going to look at the limit as theta goes to 0, cosine theta tan theta over theta. Again, the problem with this is when I plug in 0 into the tangent, that's 0. Then we obviously have 0 in the bottom. So we'll rewrite. So we'll just pull out the cosine theta and the theta for now. And we'll write tan as sine over cosine. And lucky for us, the cosines are going to cancel out. And this turns into our special limit. So this will end up being just 1. Okay, so a lot of times with the trig, break down everything into sines and cosines. Things will cancel out, and then you have 2 special limits. You have another one. It's a limit as x goes to 0 of 1 minus cosine x over x. I do believe that that one is probably 0, so if you do run into something like that, that's another special limit. Okay?